Okay, so let's think about this question. So there are many ways to find the probability. If you want to find just the probability, just imagine that you measured all 3 qubits. So the chances that you observe 0, 0, 0 is 1 over 12. Like how many? Point something, right? Point. And also, the chances that you observe 0, 0, 1 is 2 out of 12, and so on. So my way is, so probabilities of observing, so assuming that we observed all 3 qubits, 0, 0, 0 is 1 out of 12, so it's less than 10%, and so on. 0, 0, 1 is 1 over 6, and so on. So what's the chances that your qubit 1 is 1 after you're taking up measurement on 3 qubits? So these are only cases that you have 1 on the qubit 1, right? So this one and this one. So blah, 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 and then so 0, 1, 1, and 1, 1, 1. So it has chance of 1 over 6, and this one has 1 over 12. So if you sum them up, it's 1. You always get something, and it's 100%. And there will be 1 over 6 plus 1 over 12, which is 3 over 12. That's 1 over 4, which is 25% chances to get 1 on the qubit 1. So 75% you will observe 0 on the qubit 1. So that's the naive way of doing it. But it doesn't mean that you take the measurement on all 3 qubits. Like, we are assuming that we observed all 3 qubits, but what happens when you observe just one qubit, which is qubit 1? Then you collapse the state of qubit 1 only, and then you leave the qubit 0 and 2 with other states still in the superposed state. So the best way of doing this, or the correct way of doing this, is that you find coefficient alpha 0, 0, and psi 0, 2, and alpha 1, 1, psi 1, 2. So here, this 0 and 1 is the quantum state, 1 qubit state of qubit 1. Although it's in the middle, say we switch the order, switch the place of this quantum state, and I rearrange so that the quantum state of qubit 1 is on the left. So then this psi 0 and psi 1 are the 2 qubit state. Of qubit 1, 0, and 2. Okay, so these psi 0 and psi 1. So you have to find alpha 0 and alpha 1 that splits your quantum state in this form. Okay, so let's cheat a little bit. You can do those steps that we did last time, but let's cheat a little bit. As I said, that the chances that you observe 1 is whatever that is, the alpha 1 absolute value square, and alpha 0, and chances to observe 0 on qubit 1 is the absolute value alpha 0 square. So I know already what this alpha 0 and alpha 1 absolute value must be. So alpha 1, so for example, should be 3 out of 4 square root. 0. And I know that the alpha 1's absolute value must be square root of 1 over 4. So that's why I get 3 over 4 and 1 over 4 after I take a square of them, right? So you can find out what these states are. Let's try to find the psi 1 instead. Let's leave this out. So this is 1 over 2 and 1. So again, the only case I have 1 on qubit 0 is these two, this one and this one, right? So, and also I took out 1 over 2 as coefficient, so I can rewrite as like this, minus I 2 square root of 6. And as I said, I assume that I switched the order of the qubits. So my qubit 1 is on the left hand side, but let's keep the order of qubit 0 and 2. So it's 0, 1 still. So it's a 0, 1. And then let's put I here so it gets confusing. So I here, and then minus I, and 2 over 2 over 3. So it's 1 over square root of 3. And then it's 1, 1, right? So this is my psi 1 state, 2 qubit state. So is it normalized? Is the strength of this quantum state 1? Well, let's compute. So if I take the square absolute value and then square root, I square and sum them up, what I get is 4 over 6, and this one is 1 over 3. So it's 4 over 6 plus 2 over 6, so it's 1. Yes, so this is normalized state. So if you do the same thing or similar thing for finding this psi 0, you get the normalized state for psi 0 too. So what does it mean? Why do we have to do this? Because I said we only measure the qubit 1, right? So when you take the measurement on single qubit, you don't do anything on the rest of the qubit. However, since you collapse the state, the qubit that you're measuring, it affects the state of other qubits. So when you collapse the quantum state of a qubit 1, there's nothing but 1. So there's no state 0 in the qubit 1 anymore. So the rest of the qubit 0 and 2, are collapsed into this state. So after observing 1 on qubit 1, the 2 qubit state of other qubits, qubit 0 and 2, becomes this. Sorry, 0, 1, and 1, 1, right? Well, you may find something weird. So there are many questions. There could be many questions. So think about this minus I. Does minus I has to be here, or can I move minus I to the outside here? What's the right answer? If I have to write my quantum state in the superposed state of these two states, and I can move around minus I wherever I want. Like here, it can stay here like this, or I can just take out the factor of minus I and put the minus I in here. So I can write it as minus I and delete minus I everywhere here, and I can write this. So I could say, because it only depends on the probability of the observation, only depends on the absolute value of the coefficient. When I take the absolute value of this, it's still 1 over 4, right? It's still 25%. It doesn't matter whether I have I or not, or whether they have minus I or not. But then I can say that after the measurement, the quantum state of other qubits collapse into this state, right? So which one is right? Both are right. But they are different quantum states. It can be both right. I mean, if you say it's both right, that means it has both states after the measurement. But the minus I, without or with minus I, are completely different state. It's not about superposition. It's just different quantum state. So what will happen after you measure a qubit 1? So actually, we don't know. We don't know whether the quantum state is minus I here, or I here, or just minus 1 here, or nothing in here, plus 1 in that case. We don't know. But it doesn't matter. It doesn't matter in terms of the measurement. Because when you have a minus I, or minus 1, or plus 1, it doesn't affect to the probability of the observation, right? Because the term we mentioned here it's a complex number of size 1, so it doesn't affect the probability. So the answer is we don't know, and it doesn't matter. Okay. So in some sense, when you apply, then let me make a remark. So if you have a quantum state and a complex number k, where the absolute value of k is 1, so it means that our k is somehow in this form. Okay. So only way you can make your complex number whose absolute value is 1 is that you can write your complex number as an exponential form or polar form in this way, e to the power of I theta. So you don't have the radius here. Radius is equal to 1. So if you remember what you learned in the complex analysis, so here is the unit circle, and if you map a point on the two-dimensional plane, which is called the complex plane, with a complex number, you can. I think we did in the first lecture, but I'm gonna review it again. So you can identify the point with an x and y coordinate, or with a polar coordinate with a theta and the radius. But here the radius is 1, then your polar form of your complex number is this. So you have a theta degree between positive x-axis and the line joining the origin and the point. Then you can write this way. So in fact, by the Euler formula, you can write as a x plus yi format as following. So this is actually the definition of e to the I theta here. So anyway, so when you have this, then we do not distinguish psi and k psi. So I'm not saying they are the same quantum state, but it doesn't matter in our quantum computation, so we don't really distinguish their nature in the computation. So you can just say, if you have a coefficient, complex number as a coefficient whose absolute value is 1, just ignore it. Okay? So that's what I mean by it doesn't matter. Okay. Now, so another important remark is, It doesn't matter only when you multiply the complex number of absolute value equals to 1 at the whole, on the whole quantum state. But if you multiply the same complex number with the absolute value 1 in one of the superposed state, that's a different issue. So for example, let's say if you have alpha 0, 0 plus alpha 1, 1, and this must be distinguished from another quantum state, where alpha 0, 0 plus k times f1. So in other words, k means that I have e to the I theta alpha 1 for alpha pi not to n pi. So in the measurement, in the probability sense, these two quantum states have same probabilities observing 0 and 1, because the complex coefficient for the ket 1 in the psi prime has the same absolute value as the coefficient of the ket 1 in the original quantum state. So this alpha 1 absolute value is same as this. The absolute values are the same because this is 1, right? But as a quantum state, if you have only changed the second or first coefficient of the ket state and its angle of rotation, we call it angle of rotation, is not equal to pi n, which means that it's not equal to 1, then this has to be distinguished from original state. So we're not only looking at the probability, we're actually looking at the difference of the quantum complex number in between these two complex numbers. But if these two coefficients are changed simultaneously, or in other words, they rotated with the same angle, then we do not distinguish. But we do take a difference between the angle difference, we call the phase, between these two coefficients. Okay? Does it make clear? So it will appear many times when we use this, when we have to distinguish this state and that state. So when it comes, you will remember what I meant by this. But for now, what I'm emphasizing is that don't think of the quantum state something that gives the probability only. It's not about probability. It's just the consequence of having that quantum state. So if we're just about the probability, we don't really need a complex number as a coefficient. We could just have a real number, right? But the reason why we have complex number as a coefficient is because we want the difference between the phases of the ket 1 and ket 0 state. So this theta is called the phase. So we'll talk about this next, more about this later. But first, let's move on to another topic here. Let's see. So any questions here, or the quiz questions? Yes. Tensor product commutative? I don't think. Does tensor product commutative? Well, no. So if you say, okay, 0, 1, 0, that means, so this is for qubit 0, and this is for qubit 1. This is for qubit 2, right? So that's not equals to 1, 0, 0. You cannot just simply interchange the order because it will mean that the qubit 2 has ket 1, qubit 1 has ket 0, and qubit 0 is ket 0, right? So they're not commutative.
How can we extract the qubit 1?
Yeah, I did it because there's in notation no way I can separate out into the tensor product of the qubit one qubit state and 2 qubit state. So I said I assumed that my ordering has switched. I assumed that I reordered my qubits. So how do I, and what happens when I reorder it? So originally, the qubit was ordered in 0, 1, and 2. Let's say I reorder it 1, 2, 0. Okay. So in that case, my representation of this same 3 qubit state will be changed. So first of all, the first one is 0, 0, 0 because they are all the same. How about the second one? So now it becomes, I just changed the middle one, so it's 0, 0, 1, same thing. But here, now it's get different. So I put the middle one, it's the middle one on the left. So 0, 1, 1 becomes 1, 0, 1. See what I mean? Okay. So I just assume that my ordering of the qubit is switched. It doesn't matter what order it's not like physically qubits are ordered this way. It's just the representation. I just named it, I labeled it with 0, 1, and 2. So I just put it in that sequel. I can name it differently. If I name it differently and I still follow the order of the integer, then I can reorder it, right? So let's say this one. So this one is 2 square root of 3, 0, 1, 0, and so on, right? So then now I can write the tensor product of 1 qubit state and 2 qubit state because I can separate here. And the other 2 qubits, which is qubit 2 and 1, 0, are put it together. So it's easier to write it this way. Otherwise, if I leave my qubit 1 here, there's no way other than just writing all these 3 qubit state as individual pieces than writing into tensor product, single tensor product. So it's just notation problem. Okay. So I think he mentioned the important questions. If everyone understood the questions and convinced, do you have a question? Yes. You can, which part do you hear? So that part is clear. We don't distinguish it, but it's not distinguished because, not just because the probabilities are same, but because the phase difference are preserved. If you multiply e to the I theta on every superposed state, then you rotate your state in the same angle. But here, what happens is I only rotate the ket 1 state, the angle of the ket 1 state. So they have a different phase. So this one, let's say it was phase phi, but then this one has phi plus theta. So even though the probability of observing 0 and 1 on psi and psi prime are the same, they are considered as different quantum states. We do distinguish these two quantum states. So what I'm emphasizing, we'll talk about the phase later, but what I'm emphasizing is that sometimes people think that the quantum state is just for measuring, just for taking a measurement. And if it's just about taking a measurement, why do we bother having a complex coefficient? You could just real coefficient. The reason why we have complex coefficient is because this phase, the notion of phase, is very important in quantum computation, especially when we do the Shor's algorithm. So I want to emphasize that the probability is not the only reason why we write the quantum state as a superposed state with a complex coefficient. That answers your questions? Yes. Yeah. All right, so any other questions? All right, so okay, so let's start from here. Let's talk about the quantum gate. So far we talked about the quantum state, and you cannot do anything without quantum gate. So quantum computation is about quantum state and quantum gate. So let's start from the definition of operator. So an operator on a Hilbert space So this operator and Hilbert space are common terminology used in the mathematics, but in our quantum computing business, we always mention the Hilbert space for set of all n-qubit states, as we mentioned here in the before. So the operator on the Hilbert space Hn is a linear transformation we denote it as mostly U, but that's not the only notation. But if you want to mention the general operator, U is the common terminology here, common symbol here. And it sends a vector from Hn to Hn, so it's an automorphism here. And it is linear transformation, which means that Hn is a Hilbert space, which means it's a vector space. So it sends vector to vector in a linear fashion. So it preserves the linear combination of the domain space to the codomain space. And the operator U is called unitary. If we have the following notation. So let's say psi of phi is an element in our Hilbert space, then this is equals to this. For any phi, actually, so not some phi, so any phi in the n-qubits, the Hilbert space. If you take the inner product or bracket operation between the same thing, I mean, with itself, so we denote it as this notation. So phi bra U dagger. So it's not T, actually it's dagger. So it's different when you see the textbook. In any manuscript, it's not T. It's the bra of U phi. Okay, so what I mean by this is you take just bra of the transformed vector and then take the bracket with itself, and that's just the notation-wise inner product. And the unitary means that it preserves the norm of the original vector. And yeah, so we're always going to talk about the unitary operator. And the remark is, so think about the linear algebra again. So any vector in Hn is represented by two to the n times one matrix, right? So we mentioned that. So we mentioned that if you take the tensor product of one qubit state, and one qubit state is represented by 2 by 1 matrix, then if you have n qubit state, then you're taking tensor product of 2 by 1 n 2 by 1 matrices. So each time you take tensor product, your rows are multiplied. So if you have n qubits, then it becomes 2 to the n rows, but the columns are still 1. And if you have a unitary, or let's say operator on this Hilbert space, that is represented by 2 to the n times 2 to the n matrix. Because whenever you have a vector space and you have a linear transformation between the vector space, this can be represented by matrix. And the rows and number of rows and columns are the dimensions of domain and codomain space. So here it's an automorphism, so we have the square matrix. And what do you mean by unitary operator? A unitary operator is represented by two to the n times 2 to the n matrix U. We'll say let's use the same symbol here, such that U dagger U is equals to identity matrix. So here U dagger is the conjugate transpose of U. So conjugate transpose means you take the conjugate of every entry in the matrix and then you transpose it. So since every entry in the matrix is complex number, you can take the conjugate, you get different different matrix, but then you take the transpose again. All right, so let's let me make a final definition and let me give you an example. A unitary operator on n-qubit state, Hilbert space, is called quantum gate. So whenever you see word quantum gate, just imagine it's an operator, linear transformation. So it's not fancy thing that you actually go through a gate, whatever. It's not like that. It's just an operator. And if you start to think about this operator as a physical thing, you get into a trap, same trap as we saw in the entanglement example. All right, so let's give an example of a quantum gate. Well, actually, it's a definition, so it could be example or definition, whatever. So I'm not saying these are the only quantum gates, but these are the one that we can actually implement and is implemented in the real quantum computer. And it's quite useful in carrying out quantum computation. So here, let me make a numbering here. So there is something called X gate. This is the most important one of the most important one. And we denote it by X, so not U. So usually we write the operator with one letter, and in this case we use X, the capital X, and the matrix representation of X is 0, 1, 1, 0. And later when we need to describe the quantum circuit, we will use the following symbol, following picture as a representation of X gate. So there is a bar which represents the kind of a timeline that the qubit, some qubit state is running through, and then it kind of depicts the process of this quantum state on the left is passing through a gate called X and then becoming into another one. So just to make the picture of this quantum state, quantum gate. And sometimes, since X is quite used widely, they use this O plus symbol as a X gate. Let's look at more deeply into the X gate. So what X gate do is actually it sends 0 ket to 1 ket. So by the way, it's 2 by 2 matrix and it's 1 qubit gate. So there are so the quantum gates are generally a unitary operator on n qubit state, but if n is 1, then those operator is called 1 qubit gate, and this is one of the example of 1 qubit gate. So it acts on 1 qubit state, and it sends 0 ket to 1 ket, and 1 ket to 0 ket. So as long as you find out what happens when you apply the quantum gate on the base state, you figure out everything. So 0 and 1 is the base state, the basis of the Hilbert space H1. So this describes the entire action of our quantum gate X. And for example, what will happen when I apply X to plus state? So plus state is the superposed state of 0 ket and 1 ket with the positive signs and on both base state. What will happen? So yes, plus ket. So X is applying to 1 over square root 0 and 1. And it's a unitary gate, which is linear combination. As I said, linear combination by definition is one that preserves the linear combination. So X applies to 0 and X applies to 1, which means it's 1 plus 0. But still, it's the same thing as plus ket. Right? So how about minus ket? Yes, minus ket, right? So minus 1 ket, and that becomes 1 over square root of 2, and 0 becomes 1, and 1 becomes 0. So if you reorder it, and then you have to take a minus 1 to outside, so it's a minus 1 over square root so just minus 1 ket. I don't have space, so let's just put it minus a ket. Okay. So let me look at another example of 1 qubit gate. So that's called Z gate. And Z gate, of course, is written as Z. And the matrix representation of Z gate is 1, 0, 0, minus 1. And we denote that, we picture it as Z box in the quantum circuit. So far we only look at the two, but look at the matrix representations of these two quantum gates. Are they unitary by the definition of unitary matrix? So first, 1, 0, 0, 1, the dagger of the conjugate transpose of these 2 by 2 matrix is itself, right? If you take the conjugate, it's the same thing. If you take the transpose, since it's symmetric, it's the same thing. So it means that if you take the square of the X, then you should get identity matrix. So do you really get the identity matrix? if you take the square of this 2 by 2 matrix. Yes. So I don't have to carry on. How about this one? It's still symmetric, and it's still, every entries are real. So if you take the dagger, then you get the same thing. And let's take the square. What is it? Identity again, right? So they are all unitary matrix. So what does this do? So let's think about the matrix representation here. And you can think about this way for the X gate, but let's try to see what happens when I apply to the 0 gate in terms of matrix multiplication. So as I said, that is 2 by 2 matrix, and then 0 cat is 2 by 1 matrix, which is 1, 0. And what is this? 1, 0. So it means it's just same cat 0. Let's see what happens when I apply Z on 1 cat. So same thing here, but here it's 0, 1 for the cat 1. And then it's 0 and minus 1. So it's minus 1. Okay. So you may think that, okay, well, does that gate really do anything? Because it changes 1 to minus 1, and minus 1 is just another complex number whose size is 1. So as I said, if you multiply the complex number of size 1 into entire quantum state, we don't distinguish those two. But then why do we have to bother distinguishing 1 cat and minus 1 cat? So yes, but yes, that's true. If you're working only on base state, if you're working on 0 cat and 1 cat only, no superposed state, then that gate is actually doing nothing. Okay? However, let's think about what happens to the plus cat. What is it? Minus cat, right? And when you apply that gate onto minus cat, what happens? Plus cat, yes. So it interchanges the plus cat and minus cat. So the reason why I think, so you may not agree, but I think the X gate and Z gate are the most important thing among all the quantum gates because of these two special properties. So look at these 4 special identities. So here 1, 2, and here all the way up to here, and here again all the way up to here, right? And also look at this two. Z0 goes to 0, and Z1 goes to 1, minus 1, and these two. You can see that X and Z are almost identical, only differ by the bases. What I mean by that is, if you think that 0 is replaced by a plus, if 0 cat is replaced by plus cat, then and 1 cat is replaced by minus cat, and X is replaced by Z cat, Z gate, then that is exactly what it says, right? And same for others. So it's somewhat depicted in this way. So let's say we have, so it's not the completely accurate picture because I cannot draw a 4-dimensional space, which is complex plane, in a 2-dimensional actual plane. So let's say in this way. So we have 2 orthogonal base, it's 1. 2 orthogonal bases of the H1 Hilbert space. Okay, so X is actually interchanging this, and let's say we have another orthogonal basis, which is in a sense 45-degree angle difference, not in a planar fashion, but in a complex plane, it actually it's 45-degree angle difference, and one is plus ket and the other is minus ket. These are also another basis which is orthogonal to each other, and it says Z gate is interchanging between others. Okay, so in some sense, the role of X and Z are only depend on which basis you're taking for the complex, for the Hilbert space. If you take the basis of Hilbert space as 0 and 1, X is something that interchanges. But if you take plus ket and minus ket as a basis of your Hilbert space, then Z gate is actually one that interchanges these two basis states. And the other one is the one that interchanges the other basis. So really, X and Z are not an absolute gate. It only matters of it's always relativistic in terms of which basis you're taking. I think I mentioned that maybe other class that what do we mean by plus ket and 1 ket? I said it's not absolute state. It's always just the relativistic state. And as I'm saying it again, that 0 ket and 1 ket is not something that you can absolutely define it. It only matters of which state is you consider as a standard basis. And the reason why I'm emphasizing this is when we go to the quantum error correction, we need to think about the logical quantum gate, or logical qubits. And in that logical qubit state, we're not actually dealing with the 0 ket and 1 ket. We're not physically looking at the quantum state of each qubit. We're looking at in an ideal sense. And therefore, I think it's better to drop the idea of these kets are real. It's just the notation. It's always relativistic. And thinking about this one, there's a third, I think, yes, there's another yet important quantum gate called H gate. And it has a special name. So these are X gate and Z gate. They have no name, but H gate has a name. It's called Hadamard gate. And it is written as H and also depicted as plus box H in the quantum circuit. And the matrix representation of this is a bit simple, complicated, but let me write it again. So here, so we have 2 by 2 matrix with 1 over square root of 2 or minus 1 over square root of 2. Only have minus 1 here. And what it does is it changes 0 ket to plus ket and minus ket to, 1 ket to minus ket. So you can take this as an definition, or you can take this as a definition, whichever it works. So, but most physicists think this is a definition, but I don't really distinguish the gate and the linear transformation and the matrix. So I think that you can take anything as a definition here. And how about, according to this definition, what happens when I apply Hadamard gate on the plus ket? Zero ket, yes. And Hadamard on minus ket is 1. You can carry out the computation by yourself, but what happens? So it interchanges the base states, right? So if you apply Hadamard on 0 ket and 1 ket, it changes to plus ket and minus ket, so it changes the basis. So X and Z only interchanges inside the basis, but H changes the basis itself. So 0 becomes plus and 1 becomes minus and actually interchanges this. So Hadamard accent here. Okay. So these three are the most important 1-qubit gates. There are more. Any questions on this matter? So let's look at more 1-qubit gate. So here there are Y gate. They're called Y. So I don't know why they put X, Z, and Y. I think that's probably related to some discovery of that quantum gate in physical levels, physics in physics. So anyway, so Y gate is represented by 2x2 matrix like this, and then it denoted as, so the rest of the quantum circuit has the same, almost similar picture. You just put the symbol inside the box and on top of the wire here. So what does this Y gate do? So if you take, you don't want to understand the Y gate acting on the base state. Instead, the best way to understand Y gate is that it's an action of X and Z gate simultaneously. So not really simultaneously, in sequel. So let's say what happens when I apply X and Z gate. So if I do that, I'm not really applying X gate first, because when I have X and Z written in this order, what happens is I take first Z gate on the psi state, and then take X gate apply to that, the resulting state. So this is applying Z first, X second. Okay? We have to be careful about what's first and what's next. But anyway, in a matrix sense, you don't have to worry about which operation, which multiplication you do first, as long as you don't change the order of multiplication. So let's think about what happens and when I multiply X and Z together. And X is 0, 1, 1, 0, and Z is 1, 0, 0, minus 1. And this is 0, minus 1, 1, 0. So I don't care what psi is. I just want to represent my X times Z in terms of Y. And this is equals to I times Y. Minus I times Y psi. See, if I replace Y with this 2x2 matrix, I get minus I times minus I on the 1, 2 entry, which is minus 1, and minus I times I equals to 1 on the 2, 1 entry here. So I can say X times Z is equals to minus I Y. Okay, so now does this minus I really important? Well, it's important because it's how we define the Y gate, but when you take a quantum computation with the Y gate, this minus I is multiplied after you take a applying the quantum gate Y, right? So you have fixed state after applying the Y, and then you multiply entire quantum state with the coefficient minus I. And we said we don't distinguish two quantum states when we multiply the same coefficient all around, right? So this minus I really doesn't have effective result, but since we defined Y in this way, we will keep the minus I always whenever we talk about the multiplication of X and Z. But what is important is that it's not about minus I, it's about the order of multiplication. Let's say what happens when we multiply z and x. Means that we apply x first and z next. So this is 1, 0, 0, minus 1, and x is 0, 1, 1, 0. So this becomes 0, 1, minus 1, 0. And this is I times y. So you can see that x times z is not equals to z times x. It's minus times z times x. Okay, that's the important thing. So you don't want to apply the y gate because, I mean, it's not really important whether you apply the y gate or not, because you can always split it into x and z gate. Okay, so you can always rewrite your y gate as an action of x and z gate, but the order of x and z gate matters because it gives the minus 1 here. So again, okay, so if I'm going to multiply minus 1 all the way, everywhere, then what does it do actually? So actually it does something, because you don't want to apply the minus 1, and this is not the final state, and sometimes you have to linear combination of lots of operators, and this minus will change the phase of the quantum state. So you want to keep the order of x and z, and you don't want to get rid of thinking about this minus 1 here. That's very important. So it's called anti-commutative. Anti-commutativity of x and z. And again, when you come to the error correction business, this is something that is really important, and this is only thing we can detect whether we have successfully did the error correction or not. Okay, so there are lots of other gates, but we don't have time to introduce right now. So we're gonna talk about the 2-qubit gate next time, and then and also 3-qubit gates if you have time. And also what we're going to talk next time is that sometimes, mostly physicists talk about the action of the quantum gate as a rotation in some angle. And that axis is also represented as a Pauli matrix. You probably heard Pauli matrix somewhere in physics class. So I want to resolve the meaning of this. In fact, you don't need to really understand what the rotation means, but the reason why I want to try to relate these two concepts is because there are this kind of wording appears a lot in the quantum computing business. So whenever I just want you to convince yourself that whenever you have rotation, then it's the same thing as the action of quantum gate. All right, so that's for tomorrow. And if you have any questions, let me know after class, and see you on Wednesday.